Welcome back, Marauders. This video, 16.3, autoionization of water. Last video we talked about the Bronsted-Lowry definition of an acid and a base. An acid is a proton donor and a base is a proton acceptor. And we looked at how water, H2O, can act as a proton donor or acceptor. So it can act as an acid or a base. And so we're going to see autoionization of water means that if you have water, one of the waters can act as an acid, and another water molecule can act as a base. And so that means that one of these can transfer a proton to the other. So a proton can be lost by this water, making it become hydroxide, and this water can gain a hydrogen ion, making it hydronium. So when you have water, that water can turn into hydronium and hydroxide, and it does this. When you have a sample of water, most of it's still H2O, but a small percentage of it is hydronium and hydroxide. It ends up being an equilibrium, so this reaction can happen in both directions, and so we can write out an equilibrium expression. We write an equilibrium expression, remember from chapter 15, we put the products on top, so we have H3O plus on top, and then we have OH minus on the top, okay? And then on the bottom, we would put our reactants. However, our reactants are both liquids here, and remember in an equilibrium expression, you only include the aqueous products or gases. We don't include any solids or pure liquids, so water doesn't get included. So the equilibrium expression here just ends up being Kw, so it's called Kw because it's the equilibrium constant for water, and it's H3O plus and OH minus. This value Kw is a constant, and Kw is equal to 1 times 10 to the negative 14. So 1 times 10 to the negative 14 is the value for Kw. That's a really small number. So what does that tell us about this equilibrium? Do we have a lot of products or a lot of reactants? Well, since that's a small number, it means we have pretty low concentrations of your products over here, and most of it remains over here on this side. So it favors the reactants. In water, you have mostly H2O, and then just a small fraction of it turns into hydronium and hydroxide. So this works not just in pure water, but in any aqueous solution. And so since 1 times 10 to the negative 14 is always equal to hydronium times hydroxide. That means we can use this equation. If we know hydronium, we could find hydroxide. If we know hydroxide, we can find hydronium. It also means that these two are inversely related. So when one increases, the other decreases. And so acidic solutions have a lot of hydronium, basic solutions have a lot of hydroxide, but you can't have a solution that's both acidic and basic. As the hydronium increases, the hydroxide has to decrease. And if the solution were more basic, as the hydroxide increases, the hydronium would have to decrease, because these two things always have to multiply together to be 1 times 10 to the minus 14. So they're inversely related. That's pretty important. And as long as you know one of them, you can always solve for the other using this equation. The hydronium ion, H3O plus, when hydrogen ions are in water, the hydrogen ion will attach to the water and make hydronium. So hydrogen ions, which we call protons, they form hydronium in water. And so we use these two terms kind of interchangeably. Any of the equations that you see me using hydrogen ion, I could have just as easily written hydronium ion. They can be written interchangeably. So I could have also, right, on this last slide, I had the equation 1 times 10 to the minus 14, Kw, is equal to hydronium times hydroxide. I could have written that out as hydrogen ion times hydroxide ion. So we use these two things kind of interchangeably in really any of the equations that you see in this chapter. So how do we know if something is acidic, basic, or neutral? Well, we know that something's neutral if the hydronium and the hydroxide are equal to each other. And since these two things have to multiply to be 1 times 10 to the minus 14, when these two things are equal, each one of these is 1 times 10 to the negative 7. 1 times 10 to the negative 7. So if you have 1 times 10 to the negative 7 for hydronium and hydroxide, they're equal to each other and the solution's neutral. When you have more hydronium, and then you have hydroxide, then the solution's acidic. And if you have more hydroxide than hydronium, it's basic. The concentrations of these are inversely related, so they can't both be high. If one goes up, the other has to go down. If a solution is really, really acidic, it can't also be basic. They're inversely related. And so when you have an acidic solution, you know that the hydronium concentration has to be greater than 1 times 10 to the negative 7, because that's what it is when it's neutral. And if the solution's basic, you know that the hydroxide has to be greater than 1 times 10 to the negative 7. You'll never have a solution where both the hydronium and the hydroxide are both greater than 1 times 10 to the negative 7. So by taking a look at the concentration, you can figure out pretty easily if it's acidic or basic. So here's an example. The hydroxide concentration in an aqueous solution is 3.5 times 10 to the negative 9. So we have a hydroxide concentration of 3.5 times 10 to the negative 9. What is the hydronium concentration? So we want to find H3O plus. And then we want to know, is it acidic or basic? Well, just by looking at this number, we can tell right away that this solution is going to be acidic, because we know that the hydroxide concentration is 3.5 times 10 to the negative 9. For a solution to be neutral, remember, your hydroxide concentration would have to be 1 times 10 to the negative 7. Well, in this case, we have a concentration less than that, so it means we have a low concentration of hydroxide, and we're going to have a higher concentration of hydronium, so we can tell right away that this is going to be acidic. To solve the other part of the question, to figure out what the hydronium concentration is, we'll do Kw, which is 1 times 10 to the negative 14, is equal to hydronium times hydroxide. So 1 times 10 to the negative 14 is equal to hydronium times 3.5 times 10 to the negative 9. And we'll divide both sides by 3.5 times 10 to the negative 9, and you get that the hydronium concentration is equal to 2.86 times 10 to the negative 6. That's the molarity of the hydronium. And you can see that that's greater than the hydroxide, which we had at the beginning, which was 3.5 times 10 to the negative 9. So anytime you have more hydronium, you know the solution is acidic.